Hello everyone, I am here to finish out Chapter 5 with a couple of more videos. The first one is going to be dealing primarily with structural issues, just like we've been doing before. So what we've been looking at as far as compounds with stereogenic centers, we've just been looking at compounds that had one, right? We can have more than one stereogenic center, all right? As you might expect, once you start increasing the number of stereogenic centers, that's going to increase the number of possible 3D arrangements. And of course, in turn, that means we have more possible stereoisomers, right? So for first thing I'm going to do is I'm going to share with you a mathematical formula. Yay, everybody's favorite. However, this one is extremely simplified, but very useful, all right? There's a little formula that you can use to calculate the maximum possible number of stereoisomers within a given compound, or within a given general flat structure. Whoa. Don't know how to spell isomers. Okay, so the maximum number of possible stereoisomers that you can get is equivalent to 2 raised to the nth power. Okay? And n refers to the number of stereogenic centers in your structure. So, very, very simple. Okay? So, for example, if you had something like this, I won't even do dashes, wedges here, because you can tell this little part just from the flat structure. Okay, so if we look at this one, right, what's the maximum number of possible 3D stereoisomers we can make from this molecule? Well, if we look at it, let's count the number of stereogenic centers. All right, I think we can say that this carbon with the OH and the methyl group is stereogenic. It's got an OH, a methyl, an ethyl, and then this big large chain over here, so that's one. And if we look at the one with the chlorine, it has a chlorine, it's got a methyl, it's got a large carbon chain over on the left, and not drawn, but don't forget it's still there, the H. All right, so we have 2 stereogenic centers. So if we wanted to figure out the maximum number of stereogenic centers, or excuse me, the maximum number of stereoisomers we can make, just simply say 2 raised to the 2nd power, because we have 2 stereogenic centers, equals 4. So it's possible you could have 4 stereoisomers. Easy peasy, right? If you had something like this, we would actually have 3 centers. I won't go through it painstakingly with you. Hopefully you guys should be pretty good at recognizing these by now. Right? In that case, you would have 2 raised to the 3 power. To the 3rd power, gosh. And that means you could have a maximum number of 8 stereoisomers. And this can go on and on. I mean, you can have really large molecules that have large number of stereogenic centers, so you can see it gets very complicated very quickly. What we're going to do, though, within the scope of sophomore organic chemistry, we're really going to be sticking primarily, in most cases, to having 2 stereogenic centers, if, it's a case where we have to draw all of them, okay? So that's what we're really going to be focusing on here. And I want to introduce a new term to you now. Now that we have more than 1 stereogenic centers, we can have what we call diastereomers. And just like the word enantiomers, right? We said that enantiomers were non-superimposable mirror images of each other. This is a noun. right? So this is going to describe the relationship of two or more stereoisomers to each other. All right. So if we have a pair of diastereomers, for instance, what we would say is that they are non-superimposable, non-mirror images of each other. And that's something that you're going to see now that you haven't seen before, right? When we drew a pair of enantiomers, right, we said that you always have one, and the other one's always going to be the mirror image of that one, right? And if we had only one stereogenic center, that's basically 2 raised to the first power equals 2. You know, those are the only 2 stereoisomers you can draw, is that pair of enantiomers, one and then its mirror image. Well, now that we get to diastereomers, and you have more than, more than 2 possible stereoisomers, you're going to see some that are not going to be mirror images of each other, but they're still not going to be superimposable. All right, let me show you a couple of examples of these. All right, let's say we had this. Let's say we got a BR right there, we got a CL right there. Okay? Now, if you were to look at this more closely, I think you would probably be able to recognize the fact that we have a stereogenic center there and there, right? So this one has a maximum number of stereoisomers of 4. 2 stereogenic centers, 2 raised to the second power, 4. All right? So let's talk about how you would go about drawing these 4 stereoisomers, first of all. All right? Well, if you have a flat structure like this, first one's entirely arbitrary, right? We have a BR on this first one, not drawn, but we also have an H, right? So what we need to do is we need to apply those to being dashed or wedged, right? So we could put the BR on a wedge. You don't actually have to draw the dashed H. I will in this case, just so you can see it. All right, there it is. All right, now we can do the same thing for the next carbon. You have a chlorine and a hydrogen on a dash and wedge. So I want to put the chlorine on the wedge. I'm going to put the hydrogen on the dash. All right, so that's one. That's 1 out of our 4 right there. How do you get the second one? Well, easiest thing to do, draw the mirror image. Yeah. Okay, so we have that, and we have this. There we go. And we know that these guys are enantiomers of each other. Okay? All right, I'm going to do my best, and this may turn out to be a disaster, but I want to try to draw the other ones on this other little side here. All right. So keep that in mind. In fact, I'm going to go ahead and label these in case I have to erase them, so you'll have them on your paper. Just go ahead and label this one A and this one B. All right. So how do you draw the other 2? Here's a very easy systematic way to do this. Whenever you get ready to draw your third enantiomer, just simply take the very first structure that you drew, pick one of the stereogenic centers, and switch the groups. Okay? So, for instance, in this one, what I'll choose to do is I'll choose to leave this guy the same, right? But I'm going to switch the groups on the other stereogenic carbon. I'll put the Cl on the dash this time and put the H on the wedge. Only do it for one of the centers. Don't do it for both of them. That'll totally screw you up. Okay? Alright, so that's number 3. And then for the 4th one, guess what you do? Draw the mirror image, that guy. Works every time. Nice little easy systematic process. Draw one enantiomer, draw one structure, draw its mirror image. That's a pair of enantiomers. Take the first molecule, switch the groups on one of your stereogenic centers, draw that, and then draw the mirror image. All right, that gets 3 and 4. This is also a pair of enantiomers. And I'll call this one C, and I'll call this one D. All right, so that's great. In this case, we don't have just one pair of enantiomers, we have 2 of them. All right. Let me ask you this, though. If somebody were to ask you to compare the relationship of A and C, how would you describe it? Well, are they mirror images of each other? No. So they can't be enantiomers. Are they identical? Are they superimposable on each other? No. There's absolutely no way you can flip or flop one or the other to have it perfectly line up. A and C are non-superimposable, non-mirror images, so we're going to say that A and C are diastereomers of each other. A and D. Come on. A and D, diastereomers. B and C, diastereomers. I'm running out of room, but I'm assuming you guys can probably write this on your own. B and D, diastereomers, right? So, what we have here in this sample of 4 different stereoisomers, we can, depending on which ones we compare to each other, if we compare A and B to each other, they're enantiomers. If we compare A and D to each other, they're non-superimposable, non-mirror images, they're diastereomers. Okay, so that's one thing that's going to be important to recognize whenever you're doing these is, once you draw all the possible stereoisomers, compare them to each other. See if they're superimposable or not, see if they're mirror images or not. That'll tell you how they relate to each other. All right, let's try another one. Let's try a cyclic one this time. Want to make sure you guys see one of those. All right, let's say we got this. I just realized I really drew this in a bad spot. I need to plan ahead, right? Drawing on a tablet. Got to make sure I have enough room. Okay, so let's take a look at this guy. All right. Hopefully, if you look at this for a little bit, you'll be able to tell that we again do have a couple of stereogenic centers, right? Right there, we have a methyl group. Not drawn, we have the H. And what do we do for cyclic compounds? We basically divide the ring in half, right? So we have 2 halves of the ring that are definitely not identical to each other. All right, so that one's stereogenic, and that one is too. Excuse me. All right, so even though it's cyclic, we still follow the same rules that we did before. Okay? So, what we're going to do is, we know we need a dash wedge here at each of these. Now, each one of these stereogenic centers has an H attached, which you don't have to draw in skeletal form. I am going to skip drawing the H, whereas I drew it in the last one. You guys probably need to get used to seeing something like this. So, for example, here, I want to draw that methyl group on a wedge, and the H is understood to be there on the dash pointing in the back, if I draw it like this. Same thing with this, the OH. Okay, so there's one. I can draw its mirror image. Don't forget to put the double bond in the right place. Remember, this is a reflection, so it needs to be reflected in the proper spot. These guys are enantiomers. Come on. And then what do? We pick one of the carbons, one of the stereogenic carbons. We switch the groups. I'll just do it with the OH. and then draw its mirror image. Didn't leave myself much room there, but hopefully you can still see it. Boom. There we go. These guys are enantiomers. Again, we could label these A, B, C, D, and hopefully you can tell, which ones have diastereomic relationships, right? A, it's going to be the same basic pattern as last one. A and C definitely are not superimposable. They're not mirror images. Same thing for A and D, B and C, B and D. Okay? All right. Very good. Now, that's how you draw them. Now, just like at any other point, it's important also to be able to recognize the configuration around stereogenic centers, even if you have more of them. Excuse me, even if you have more than one of them in a particular structure. All right, I'm going to go back to the previous example. Right, I'm actually going to redraw these, and I'm going to be, lazy / efficient, depending on how you want to describe me here. And I'm just going to draw these heteroatoms. I'm not going to bother drawing the H's in the back, even though they're understood to be there. All right, so there's that. We had this. Let's see, we had this. Whoa, I didn't mean to go into red all of a sudden. Although maybe I should. It was quite pretty. So we switch the groups on the middle carbon and draw the mirror image. Okay. All right, so whenever you have more than one stereogenic center in a particular structure, you have to assign configuration around every individual stereogenic center. So if you have 4 stereogenic centers in a molecule, guess what? You got to do RS configuration around each one of them. Okay, so that's what we're going to do here. Each of these is going to have 2, and so I'm going to show you how to do it. And honestly, there's really no new rules. You treat it the same exact way that you did before. However, I can show you a little bit of a shortcut in here, an additional shortcut to what we've already learned. Sorry, losing my voice a little bit. All right, let's start in structure A over here. All right. All right, if we look in structure A, let's just go left to right. The first stereogenic center we have is the one that has the bromine attached. All right, so notice in my initial arbitrary drawing, I kind of did this smartly because what I did was I intentionally drew this with the lowest priority group, the H, in the back. If I were to draw that skeletal structure H, there's nowhere for it to go but a dash, right? So that makes my life a little bit easier. So it's already arranged in the right position. If it was not, you would either have to flip the molecule or apply the sort of shortcut cheat method that we learned last time. All right, but let's see. We have a Br, we have a carbon, and then we go out, this carbon has a Cl, and we have a methyl group. I'm going to say definitely that Br is number 1. This large group is number 2. And the methyl group is number 3. So if I do that, we go clockwise, we see that the configuration around this one is R. Okay. The next stereogenic carbon is going to be the one in the middle, the one that has the Cl. All right. We have a Cl attached. We have an ethyl group attached. And then we have another ethyl, but the one that has a Br coming off the middle one of the carbons, right? I think it should be easy to see the Cl is number 1. This way we have a carbon, this way we have a carbon, that's a tie. However, the carbon on the left is also attached to a Br, whereas this one on the right side is not. So this guy is going to be number 2, and ethyl group, wow, Come on, stylus. You can do it. That's 3. So 1, 2, 3. This one's also R. Okay? It's just standard rules. All right. Now, you can go through and do this for every single one of the stereogenic centers remaining, and I trust you should be able to do that if necessary. However, when you have them all drawn out like this, there is a much easier way you can use through just common sense and logical reasoning, right? We said that whenever you drew an enantiomer, stereogenic centers have opposite configurations than their enantiomeric partner, right? So, if we look, and I know this is messy, if we look in the first structure, the carbon with the Br had an R configuration, right? Well, and in its enantiomer, shouldn't it be the opposite? You betcha. So in this case, we know that's going to be an S configuration. All right. The carbon with the Cl also had an R configuration in the first structure. That stands to reason it should have S. And there you go. You figured it out. All right. Let's take a look at C, right? C is going to be diastereomic to A, but we can still figure it out even without doing the exact configuration analysis. All right. Let's take a look at the first one again, the first carbon, the carbon with the Br. Now, that Br is still pointed in the same direction, right? We actually didn't switch groups at all. So, should the arrangement around that Br change? No. That is still going to be R, right? We haven't changed anything around it. Now, the middle carbon here, the one with the Cl, that's a bit different, right? Because in the first structure, we had a Cl on a wedge. Now we have it on a dash. Well, if we switch the groups, doesn't that mean it'll have the opposite configuration? It absolutely does, right? So you can tell that that should be S. And then we have the mirror image, the enantiomer, which is structure D. Again, carbon with the Cl, if it has an S configuration on one side, the mirror image should have an R. So that's R. Carbon with the Br in structure C has an R configuration. Its mirror image should have an S. Viola. It works very well. Tricks like that can save you a bit of time and also can save you a little bit of sanity sometimes. Because I know flipping molecules is definitely not an easy thing to do. So there are some other very good logical ways of looking at it that can help out. Okay? All right. All right. One thing you might notice is I kept saying, I kept referring to something when I was talking about figuring out the number of stereoisomers that you have, using the 2 to the n power formula. I always kept saying maximum number of stereoisomers. I didn't say just the number of stereoisomers. That's because you don't necessarily always get to that number. Let me explain. All right. What we're going to do here is we're going to introduce the concept of something called a meso compound. Sorry, I made a bad C here. It's bothering me. All right. A meso compound is going to have more than one stereogenic center, first of all. However, it's going to be, come on. Okay, I'm literally drawing here. My stylus is not responding. Sorry about that. But it is achiral. And that's something we haven't seen yet, right? Everything we've seen so far with stereogenic centers has been chiral. All right. Remember the guidelines we gave back at the early beginnings of the chapter. We said if you had 0 stereogenic centers, you're always achiral. If we have one, you're always chiral. We said if you had two or more, it depends. So this is kind of where we get into that depends moment. All right. Here's a really good example. Okay, let me take this off the screen. All right, let's take a look at this guy. Okay. All right, now if we look at this, we should, after analyzing this and checking all the carbons, we should be able to identify a couple of stereogenic centers. We got one. Come on, my stylus is really having problems today. There's one right there. There's one right there. Okay. So we go about our business and we can draw all the possible stereoisomers. Since we have two stereogenic centers, our maximum number is 4, right? All right. Well, let's take a look. Here's what I'm going to do. I'm going to draw one like this. I'll go ahead and make them trans the first go around. Mirror image. Okay. All right, so what do we want to do? Well, we take, to draw the third stereoisomers, remember we take the groups on one of the stereogenic centers and switch. All right, so I'll just do that on the right. So we get that as our third one. And then we draw the mirror image. All right, now take a look at this for a second. Do you notice anything kind of strange here that you haven't seen in any of the other examples? Spoiler, spoiler, spoiler. Yeah! Don't those last two structures look pretty similar? In fact, perhaps identical? That's because they are. These are the same exact compound. There's no difference, right? This is easy to see because you could literally take that second compound, the mirror image, and slide it directly over the first one, and it would be perfectly superimposable, which we know indicates an achiral compound. Right? This would be a good example of a meso compound. So we wouldn't have an A, B, C, and D here. We would just have A, B, and C. Right? We don't get 4 distinct stereoisomers, we get 3. A and B are enantiomers to each other, A and C are diastereomers to each other, B and C are diastereomers. There is no D. Right? And this has, when we see a meso compound, you see traits that are common to achiral compounds. Number one, if we did hypothetically call this D, right? D is perfect, like we said, D is perfectly superimposable on its mirror image, C, right? Superimposability is indicative of achiral compounds, as we learned in the past. Also, we learned that achiral compounds will have a plane of symmetry. Well, if I were to take one of these structures here and just slice it right in half, I think it's pretty easy to see that we can get 2 identical halves without any problems here. All right, so that's what a meso compound is. All right, and those will pop up from time to time when you least expect it. So be sure whenever you're trying to actually figure out, did I get 3, did I get 4, whatever, take a close look to see if any of them are meso or not. Sometimes it's obvious, like that one. Sometimes it's not as obvious. For example, let's say we had this guy. Come on. All right. All right, if we take a look at that one, it should be apparent that we have stereogenic centers at each of the carbons with OH groups. All right, so let's go about drawing them. I'm just going to start off putting them both on wedges. Mirror image. And there we go. Now, if you look at this, you might be tempted to say, oh, well, these actually look kind of similar. Maybe this is a meso compound. Well, whenever in doubt, try it. See if there's any way that you can slide them over and superimpose them, or maybe flip one of them over and then superimpose them, or maybe twist around the carbon-carbon single bond. What's surprising about this one is that you could try doing this all different ways. Neither one of these two would ever superimpose. Right? In this case, the wedged OH groups line up, but the carbon backbone doesn't if you just slide it, right? So what you could try to do is sort of flip it over so the backbone's matched, but now the OHs are pointed in opposite directions, right? So there's literally no way that you could do this and get... I promise I don't have coronavirus, by the way. I literally just have a cold that I'm almost over. But yeah, no, it's not corona. I know you hear me coughing quite a bit. All right, these guys are enantiomers. Okay? Now, let's take one of those. We're going to switch one of the groups here. We'll do this one. And draw its mirror image. All right, now in this case, they probably look a little bit more different than each other than A and B do, right? And certainly if you took, I'll just label these C and D. If you took D and tried to directly slide it over to superimpose on C, it's not going to work. However, let's say you had an imaginary spatula that you could scoop it under the sort of the bottom part of this, and you could flip it over like a pancake. All right? When you do that, that would flip the carbon skeleton, the carbon backbone, right? The 4-carbon chain, and that would have it match up perfectly with C. This OH, when you flipped it, would go to a wedge. Yeah, that matches up here. This OH, when you flip it over like a pancake, would go to a dash, and that's going to match up here. So yeah, in this case, there really is no C and D. There's just C because this is a meso compound. So sometimes they're a little bit easier to see than others. Other times you will have to do some molecule flipping and or some rotation around carbon-carbon single bonds to kind of recognize what's going on. All right, so be sure to take a close look at those whenever you're drawing your structures. There's lots of good practice problems in your book, so please be doing those in addition to your sapling. All right, I'm going to cut this video off here, and then have one more that I'm going to make, and it's going to have a very much a different tone, much more mathematical, which may be good or bad news to you, depending on if you like math or not. Until then, I will see you later. Bye-bye.